the analysis portion starts with the titration. So we take the complex we made, 1.048 grams of it. It says obtain about 0.3 grams. Not important to get exactly 0.3. What is important is you know how much you obtained. And so let's suppose I scoop out of here 0.309 grams of that actual complex. That would go in a data table that surely you have written down. This is the mass of the complex. Analyzed 0.309 grams. Again, I write down all three decimal places that the balance gives me. And I don't forget that a floating decimal here will not be viewed upon favorably by anybody, anywhere, any place on planet Earth or in the Milky Way galaxy for that matter. So I've got 0.309 grams. I dissolve it in some water. 0.309 grams of this nickel complex is dissolved up in some water. And then I prepare a burette with some hydrochloric acid. In fact, when you pick the bottle of hydrochloric acid up, the stockroom, they're great people in the stockroom. They have figured out what the molarity, what the concentration of that HCl is that you're actually using, and they will have labeled it on the side of the bottle. And so we would read exactly what the molarity or concentration of that HCl is off the bottle, and it happens to be, for this particular example, 0.1326. Notice that I put my unit molar down. By the way, most instructors, as you know, don't underline molar, but us really, really old people do that. So you'll have to get used to that until all of us real old people are all gone. Okay, so now I have a burette that has some 0.1326 molar HCl in it, and I'm going to slowly add the HCl. There's an indicator that I put in, and what you're really doing with this titration is you're analyzing your complex for how much ethylene diamine is in the actual complex that you made. We're going to see that reaction in just a moment. But there's a fantastic color change that takes place. Your reaction starts out where it's very nice in blue. You add HCl till where one drop, bam, turns the solution yellowish. And when that occurs, you have actually neutralized all the ethylene diamine, and we might be able to calculate how much ethylene diamine was actually in the complex that we analyzed with this particular titration. So with any titration, I always write down the initial burette reading. How many decimal places do I read a burette to? We've been through this with sodium hydroxide. I read a burette to what? That's right, 2 decimal places. So my initial burette reading is 2.78, probably right in there somewhere. I slowly add the HCl till one more drop gave me a color. What was that called when the color? That's called end point, right? The end point of the reaction. And so the final burette reading is 29.42 milliliters. And we learned on the sodium hydroxide lab how to get how many milliliters of HCl was actually added, right? I'm not even going to show you that calculation. That's so trivial. Get your calculator out. You know that the final burette reading minus the initial burette reading will give you the burette reading, the volume added from the burette every single time. Remember, 2 decimal places minus 2 decimal places begats 2 decimal places. So if these two numbers happen to be the same, there's a 0 in that second decimal place. Don't just ignore it. You have to be smarter than your calculator. Okay, what did you get? How much volume of HCl did you actually add? You added 26.64 milliliters. That was the difference between the two. And now the question is this: well, how many moles of HCl was actually added? Now we're going to get into the harder part, the calculation stuff. So I'm going to go back and forth from this data table to what these numbers actually mean. Are we all okay so far? So I've got 26.64 milliliters of that 0.1326 molar HCl added. the question I have to figure out then is, how do I get moles of HCl added out of the burette? One of the most useful relationships of all times. In fact, I just changed my mind. I'm going to do it on this board right over here. Okay? One of the more useful relationships that you will ever have in chemistry is the fact that the molarity of a substance times the liters of that substance equals moles of that substance every time. Do I have the molarity of the HCl? Yeah, actually I do, don't I? And I wrote it down right off the bottle. So I have 0.1326, forgot my 1 there, 1326 molar HCl. Notice I wrote molar HCl. I didn't leave the HCl. That'll cost you points. You have to have M units attached every single time, no exceptions when you're doing a calculation. And isn't it true that molarity is moles per liter? Right? We've learned that. This molarity is really moles of HCl per liters of HCl. That's what molarity is, right? Moles per liter, okay? Times liters of HCl. Do I put in 26.64? Nah, you know better than that. What do I have to do to convert that from milliliters to liters? Yeah, you know, divide by 1,000, right? So I have what? 0.02664 liters of HCl. You see why this works, don't you? Liters of HCl cancels, and that gets me moles. So write down, get your calculator out. You've got to do this with me. You can't just sit there and watch me and expect you to know how to do this when you write your letter. Get your calculator out, run the numbers yourself. What number just showed up on the display of the calculator? Yeah, did you get 0.003532464? Yeah, that's what I got. You going to write all those digits down there? What is that, like 9 or 10 digits? No, absolutely not. Write it to the correct number of significant figures, but that number, that big long number, that 0.003532464, store it in your calculator because we're going to recall it for the next calculation. So store it, but what would you put on your data table so you don't get dinged for significant figures? Well, this is 4 sig figs, 4 sig figs. So what do we got here? Did you get that number? That's the correct number of significant figures. So that's what I'm going to put in my data table, 0.003532 moles of HCl. Are we all okay so far? All right? No problems up to this point. That's moles of HCl that has been added. It's not a very good 5. Okay? Now, what do I do with that number? Well, what I have to do with that number is to know what actually took place in the beaker itself when I was adding HCl to my nickel complex. It turns out that ethylene diamine is a base. It's a good Lewis base in that it has these NH2 groups, and NH2 groups pick up a proton, just like ammonia picks up a proton to make ammonium. These ethylene diamines do the exact same thing from the complex. So what you're really doing is you're destroying the complex that's in your beaker, and you're actually tying up the ethylene diamines with the HCl, and you're doing it by this reaction right here. Here's actually what is happening inside the flask itself. The ethylene, what is ethylene diamine again? You remember, it's NH2, CH2, CH2. That's ethylene diamine, isn't it? That's En. Okay. We've seen this before. Right, that's ethylene diamine. The ethylene diamine is reacting with the HCl, and the HCl comes over here and protonates that nitrogen, and I get that picks up a charge, doesn't it? When I pick up a proton, I pick up a charge. Now, question. Is this nitrogen any different than that nitrogen? They're exactly the same. So is it possible for HCl to neutralize or essentially attach a proton to that nitrogen? Will this nitrogen? Yeah, the same thing will happen on the other side, right? And that one will be positive too. Well, if that's true, then you tell me, is this reaction balanced? It looks like it's going to take 2 protons or 2 HCl's to pull this off. So to balance this reaction, 2 HCl's will be required to neutralize 1 ethylene diamine. All right? It's because ethylene diamine's bidentate. Okay? Is this reaction balanced now? Not quite. It's getting close, right? There's 2 chlorides left over on the right side. Are we all okay so far? You will see some people will write this like that, right? I kind of prefer that because that really kind of should. You could even call this 2+. I think the lab manual actually does that. In any way, shape, or form, you got to show me that the ethylene diamine is protonated with 2 different protons. Any way you want to do it, that's correct. Are we all right so far? Okay, now how does that help me? Well, I have the moles of HCl that were added from the burette to neutralize the ethylene diamine. How do I go from one substance to another? I go by a mole-to-mole conversion, don't I? So if I have moles of HCl, I might be able to calculate moles of ethylene diamine. And if I can calculate moles of ethylene diamine, is that not step 1 of getting the empirical formula? Yeah, it is. All right, so here we go. Let's start with our moles of HCl. Remember, the number that I'm going to use is the stored long number in my calculator. So I have 0.003532 moles of HCl. Again, now notice something here, right? I didn't just put moles, I put moles of HCl because I do not want to lose points throughout this whole entire lab report because I utterly refuse to attach what the moles of it actually is. Moles of HCl. And again, this is straightforward stoichiometry. Done a lot of this in class, I know. We got moles of HCl are to moles of ethylene diamine. Hey, see if you can go fill that in. There's a reason why we wrote this reaction. What is the stoichiometric ratio of HCl to ethylene diamine? Looks to me like what? 2 to 1. So I recall this number from my calculator, and I divide it by 2, and you tell me what just popped up on the old calculator. Did 0.001766232? Yeah, that's where we're all getting, that big long number. Write it to the correct number of significant figures, but store that number in your calculator for later use. What did you get for the correct number of significant figures? 0.001766 moles of ethylene diamine in my complex. Are we all okay up to this point? Now, that is 4 sig figs is the correct number of significant figures, correct? Yeah, but by the way, the correct number of significant figures is brought to you by the volume of the HCl and the molarity of HCl. What if just listen, what if the molarity of HCl was given to you with only 3 sig figs? Would this still have 4 sig figs? You'd be down to 3 sig figs, wouldn't you? So you're going to have to adjust your answer based on the data given. If this HCl molarity is given to you as 3 sig figs, then this has got 3 sig figs. If it's given to you in 4, then this is 4 sig figs. What if this was 5 sig figs given to you? Well, it'd still be 4 sig figs because of the volume, right? So you have to know how to do significant figures to be functional and employable out there in corporate America. All right. So I am 25% of my way through figuring the empirical formula of this problem. We said that if you get the moles of all 4 species, then it's really more or less a cakewalk of getting the empirical formula at that point. I now have the moles of ethylene diamine. Is that not true? So I better put that thing in the data table to the correct number of significant figures. Right, moles of ethylene. ethylene diamine. So far, so good. Now, for reasons I don't yet understand, somebody wants me to calculate what that is in terms of grams. What does this moles of ethylene correspond to in terms of grams of ethylene diamine? Don't know why that is. That's going to become obvious to you a little bit later. But to be honest with you, that's not very hard to do. Let's do it together. Remember, I'm using the big long number that's stored in my calculator, right? And I do what? How do I go from moles of ethylene diamine to grams of ethylene diamine? What do I have to have? I have to have the molecular weight of ethylene diamine, don't I? So I put moles of ethylene diamine in the denominator to cancel with it there, right? Grams of ethylene diamine. So what do I have to get the molecular weight of? Do I have to get the molecular weight of that? No, that's not the ethylene diamine that's in the complex. That's how it wound up after I analyzed it. I got to go add up 2 nitrogens, a couple of carbons, and 8 hydrogens, and get them up. Go do it. Go push pause, get yourself a drink of coffee, and you come on back with the molecular weight of ethylene diamine all knocked down. Don't you round off atomic weights either. What'd you get? Find it in my notes. You got 60 something or other, you did it right. And I got 60, depending on your periodic table may have a little bit different periodic tables are rounding a little differently. But I got 60.09892 on the particular periodic table. You should have gotten something very similar to that. Moles of ethylene diamine cancels, and I wind up with what? What did you wind up getting? Did you get like 0.106148? 636. Are you going to write all 10 digits down in your lab report and lose points on sig figs till the cows come home? No way, Jack. You're going to do what? You're going to write to the correct number of significant figures. Looks to me like that's going to be 4 sig figs. So, however, what am I going to do with that 0.106148,636 number? I'm going to do what? Stored in my calculator. I'm going to need it a little bit later on. Right? So let's transition that number over to my data table. 0.1062 grams of ethylene diamine. Are we all okay so far? Okay, we're moving along nicely, and we're actually doing a very good job of this. And we're learning how to get the empirical formula. Of the complex. Okay, next video we'll work on copper.